Hello and welcome to the Chemistry Academy. In this video we're going to go over nuclear chemistry in relation to the National 5 chemistry course. So to get started, why is it even called nuclear chemistry? It's because all of this stuff occurs within the nucleus of the atom. Okay, so the outer electrons that we usually look at when we look at bonding and ionisation, they don't take part in any of the radioactive or nuclear decay that happens within atoms. It's all stuff from within the nucleus, so our protons and our neutrons that take part in this. Why do atoms undergo nuclear decay? Well, that's because the atoms are unstable. So what tends to happen is if we've got lots of positive protons close to each other in the nucleus, they will repel each other because like charges repel, and so that creates an unstable nucleus. This is then why the nucleus will emit parts of itself in order to try and provide some form of stability. So try and prevent there being lots of positive charges close together. The nuclear decay or radioactive decay is a spontaneous process, so the rate of it is not affected by any of the normal conditions that we look at that affect rates of reactions. So things like temperature, concentration, particle size, none of these things will affect the rate of the radioactive decay. Each individual radioisotope has a set rate of radioactive decay, and that won't change regardless of the conditions that you put the radioactive source in. Okay, so it won't be affected by a change in temperature or a change in pressure or anything like that. It just always stays the same. There are 3 types of radioactive decay that we look at in National 5 chemistry. We have alpha, beta and gamma. So we're firstly going to look at how these are written within a nuclear decay equation, like some of these ones down here that we're going to come on to in a minute. So alpha can be written with the Greek letter alpha, or it can be written as a helium nucleus. You won't always see the charge here, sometimes you will just see it written like that, but I'm just putting on the charge for completeness. So alpha radiation is the loss of 2 protons and 2 neutrons from the nucleus. So it is the largest, in terms of size, type of radioactive decay that we get. And like I said, the nucleus is emitting 2 protons and 2 neutrons, which is why the radioactive decay gets given an atomic number of 2 to represent the 2 protons and a mass number of 4 to represent the 2 protons plus the 2 neutrons. Because there are only protons and neutrons being emitted there, the charge is overall positive. It's got overall 2 positive charge because of the 2 positive protons that are being kicked out. Neutrons, remember, are neutral, so they don't have any charge associated with them. So it's just those 2 protons that end up making the alpha particle a 2 positively charged particle. If we then have a look at beta, so beta can be written with the Greek letter beta, or it can be shown as an electron. Now, this is not one of the electrons from outside of the nucleus that is being emitted here. What actually happens in the case of beta radiation is that a neutron splits up into a proton and an electron. The electron gets kicked out of the nucleus and the proton stays, which is why the atomic number of the electron is -1, because an additional proton has been added to the nucleus. So remember, this is what you're emitting. So if what you're emitting is leaving an extra proton behind, then that's why the atomic number of the radiation is -1. It'll make more sense when we come on to look at how the emission of this decay changes the radioisotope. And it doesn't have a mass because electrons don't have a mass. So in the case of beta radiation, a neutron splits up into a proton and an electron. The electron gets kicked out and the proton stays in the nucleus. You don't need to know that that's what happens when beta radiation happens. You just need to know what the beta radiation looks like and what change it would cause onto the radioisotope. Also, the beta radiation is overall negative charge because electrons do have one negative charge, as we know from our time looking at atomic structure. Then lastly, we've got gamma. Gamma radiation doesn't have any mass or any atomic number associated with it. It is just energy that's emitted from the nucleus in order to try and stabilise itself. So it doesn't actually cause any change to the radioisotope in terms of its structure. It's just the emission of energy. If we move on to then what each one's stopped by, so the alpha radiation, because it's the biggest, it's the easiest to stop because it doesn't have as much of a penetrating power. So it can be stopped by a thin sheet of paper, or in the medical context it could be stopped by your skin. So alpha radiation cannot penetrate your skin either, if you think of your skin as being like a sheet of paper. The beta radiation, that can be stopped by aluminium foil, so it can penetrate paper, but it can't go through a piece of aluminium foil. And then gamma can penetrate both paper and aluminium foil, but it only gets stopped by either a thick sheet of lead or a really thick piece of concrete. So you'll see this diagram quite a lot in your exam where you've got paper, aluminium foil and lead or concrete, and it will show you the different types of radiation and which the lines. Quite often you're asked to identify what type of radiation's been emitted by each line. So alpha is the one that gets stopped by paper, beta is the one that gets stopped by the aluminium, and gamma is the one that gets stopped by the lead or the concrete. If you know anyone that is a radiographer and does x-rays in the hospital, they actually wear a lead vest in order to protect them from excessive exposure of radioactivity, because as we can see, the lead will stop all types of radioactivity, so it helps prevent their vital organs being exposed to any unnecessary radiation. You will also sometimes see a diagram of this experiment up here too, which again you're asked to identify a lot of the time the types of radioactivity that are being emitted based on where they're travelling. So because gamma has no charge, it just goes straight through, it's not affected by either of these charged plates. Alpha, because it is positive, will move towards the negative plate. Alpha, because it is larger, it does take a bit longer to travel towards the plate. And then beta, because it is negatively charged, it travels towards the positive plate, and because electrons are very small particles, it travels there quite quickly. So those are the two experiments that you'll see quite a lot in your exam, so just make sure that you're familiar with them and what they're actually telling you. If we then look at this column here, this is probably the most useful one when it comes to these nuclear decay equations that we're going to look at in a minute. This is how the emission of this radioactivity or radiation changes the structure of the radioisotope that is emitting it. So if a isotope emits alpha radiation, then what happens is the mass number of the isotope will go down by 2 and the mass number will go down by 4. Okay, and like I said, we'll use this for some of our examples here in a minute. If the particle is emitting beta radiation, the atomic number will go up by 1 and the mass won't change. And if you're emitting gamma radiation, there's no change to anything, it just stays as the same thing. Like I said, it's just emitted some radioactive energy from within its nucleus. So we're going to use this column to help us down here. So this is where we're looking to complete the nuclear decay equations, and you're usually asked to find out some missing particles. Normally it'll be asking you to identify X or whatever, but I've just put them as question marks here. So the key thing here is that all the numbers on the left have to add up to the numbers on the right. So what that means is that if you've got 84 as the atomic number here, then whatever the atomic numbers are on this side need to add up to 84. So sometimes it can help to do like a squiggly line in the middle of the arrow, just so you make sure that you know which numbers are on each side. So here we've got 2, so to make that up to 84, we would need an 82. That means that whatever this particle is element number 82, and we'll look that up in a minute. In terms of then the mass number, so on the left-hand side, the mass number is 211. So this side, the right-hand side, also needs to add up to 211. So if we do, what do we need to add to 4 to get up to 211? That would be 207. Okay, so then the last thing we need to do is work out the symbol. So if we look up number 82 on the periodic table, we will find out that that is lead, so then that would end up with the symbol Pb. So we can see that when polonium 211, because that's what the radioactive isotopes tend to be called, their element plus the mass number afterwards. So polonium 211 will undergo alpha decay in order to produce lead 207. Okay, so that's us completed that nuclear decay equation. However, the other way you can do it is by bearing in mind this column here. So if we know that the polonium is undergoing alpha decay, we know the the atomic number is going to go down by 1, which gives us our 82, and the mass number is going to go down by 4, which gives us the 207. So you can do it either way, it's up to you. I personally prefer to know the change that each decay causes because it helps us in some other questions, as we'll see in a minute. But it's up to you if you just want to make sure the numbers on both sides add up to the total number. If we go to this next example here, we've got radon 224. This time it's undergoing beta decay, and we can see that because it's written as beta decay would be. So then we're trying to find out what would be made instead, like once it's undergone the decay. So when radon undergoes beta decay, the atomic number is going to go up by 1, so it's going to go up to 89. If we just then double check, 89 plus minus 1 is essentially 89, take away 1. That gives you 88, which matches the 88 on this side. There's no mass number change when you emit beta radiation, so the mass number is still going to be 224. And element number 89 is actinium, so we put the AC state symbol there. This one down here is a bit different. This is where a neutron has been emitted. Sometimes you will see this. It's not one of the decays that we typically look at, but sometimes it can be given to you in the context of these nuclear decay equations, because you can work out what was formed just by doing the how does everything add up on both sides. So we can see there's no change to the atomic number here because there's a 0 there. So that means that 95 still stays as 95. And then the mass number, we've got 141 on this side. To get this to add up to 141, we would need to, do 240, not 141, 241. Okay, so you can see here, if we just double check, 1 plus 240 is 241. Okay, always do a double check at the end if you're doing the adding up, because quite a lot of the time people do 241, they see the 1 and then they add it on instead. So if we do our double check, we'd see that that was 243, which doesn't match there. So just do a wee double check at the end. And because the atomic number is not changed, that's still going to be americium. Okay, so that's how you do the neutron decay. These ones over here, this one here is looking at what decay has actually occurred. So if we have a look here, the atomic number has gone up by 1. So we know that that's a sign of beta radiation. The mass number also hasn't changed. So what we can do, if you don't remember this column, you can look at what, again, doing the adding up on both sides. So this side's 223. We've already got 223 here, which means this must have a mass of 0, because otherwise they wouldn't add up to equal each other. This side's 87. Over here we've got 88. What do we need to add to 88 to get to 87? We need to add minus 1. So then we end up with our mass number and atomic number that would show us that we have emitted beta radiation. So that missing question mark this time was in fact beta radiation. Sometimes you'll also get asked to do where you're given the nuclear decay product side and asked to work out what radioisotope you started with. Again, it's just the adding up. So 89 plus 2 would be 91. And then 227 plus 4 would be 231. And if we look up to see what element 91 is, element 91 is protactinium, which has got the symbol Pa. Okay, so it's all just about everything on the right adding up to what's on the left. This last one here, you can see the americium 241 has emitted gamma radiation. Like I said, there's no change to anything when gamma radiation gets emitted in terms of its structural makeup. So that means we would still have americium 241. Okay, so this gives you a summary of all the different types of nuclear decay that we get, the experiments that you often see in the chemistry exams in relation to these types of decay, and how to finish off your nuclear decay equations and identify the missing substances. If you're looking for help with half-life calculations and looking at use of radioisotopes within different contexts, then you can go and check out my other video on that. I thought I'd leave it as a separate one as to not make this video too long. So if you found this useful, please give it a like. Don't forget to subscribe, and I'll see you again soon.